Section 3.6 here is going to talk about the absolute value function. It's going to talk kind of a mishmash of ideas about it. And again, not a ton of examples, so let me kind of take you through here. So you remember what the absolute value is. In math language, somebody said, hey, I just want to know how far -3 is away from 0. So if I'm trying to say, how far away am I from 0, there's actually two numbers that are 3 steps away. I could be standing at 3 or -3. So suppose I had this equation here. So the absolute value of x is 3. Well, what number is inside of there? Well, it could be 3 or -3. And so what happened was some mathematician said, I just want some kind of abbreviation that says I'm interested in knowing how far away I am from 0. So that's just a distance. It doesn't matter if you're a positive number or a negative number. And so what they came up with is these absolute value bars. All of this says right here that I am how many steps away from 0. Now, if you have it here, if you just remember, the magical power of these absolute value bars is that they make anything a positive. But the reason is because we're asking how far away are we from 0. Now, we're going to see toward the end here that when we work it, we're actually going to, if we're trying to solve an equation with an absolute value, we're going to work it twice. Because it is possible that we have a positive value in there, or maybe it's a negative value, so we'd have to work 2 times. Now, as a function, the best way to define this would be like this is as 2 different lines. Do you remember this shape? Do I have it here? No. So this shape, this is the V shape. So it's a V on either side. So look what they've done here. They've called it a piecewise function, where if you're on the right side, when your x's are greater than or equal to 0, you get x. Well, that's just up 1 over 1, up 1 over 1. And if you're on the left side, when x is less than 0, you've got a negative slope. So you're going be up 1, back 1, up 1, back 1. And so that's where the v comes from. And so if you need a definition of that function, it's best defined here as a piecewise function. Okay, now I find this illustration very, very confusing. But so I'm going to just tell you the point, especially to jump right into this. But what they're going to say here is all of this point is, hold on, I can't even remember the point. Yeah, the manufacturers are saying that, that these capacitors need to be within a certain range. Okay, so they found that it has to be within 5% of this range. Now here's all that matters. We want to be within 34 of 680. So every time we check one of these capacitors or resistors, we want it to be within 34 of 680. Well, normally when we do an absolute value, we're saying, okay, how far away are we from 0? When we take the difference, we're saying, how far away are we from this number here? So when I turn this into x minus some number, I'm now saying, okay, how far away am I from this number here? It can be any number you want. So how far away am I from the number 2? Now, this is how far away I am on either side, because that's what an absolute value does. So how far am I away from the number 2? Here I am asking, how far away is my capacitor from the number 680? And what this story is saying is, I have to be within 34. Well, within in math language means I'm less than or equal. I've got to be within 34. Okay, so let me show you again here and see if this helps. So I want to be within 20 points of 80. So I'm not trying to see how far away I am from 0. I'm trying to see how far away I am from 80. And I need to be within 20 points. So the absolute value is telling me whether I'm within 20 on the upside or 20 on the low side. It doesn't matter because that's what an absolute value does. It doesn't care whether it's a positive or negative, it's just measuring that distance. So once again, it's x minus some number. If I've got this here, I'm saying, okay, how far away am I from the number that I'm putting here? Well, I want to see how close I am to the number 80, and I want to be within 20. Okay. Yeah, I don't. Okay, this is just talking about a shift here. So, all right, so this is translations like we did before. I start with the original function, and they're saying, all right, what have we done to it? How have we transformed this original function? So I've started with the function f of x equals the absolute value of x. Now, it normally starts right here at the origin. So what have I done to it? It's gone 3 to the right. So remember how we would do that. 3 to the right. So negative moves you to the right, even though that's kind of counterintuitive. Moves you to the right. And then the whole graph has been moved down too. Okay, now it looks like we're done, right? But if you look back at this picture, do you see what's happened? This is some kind of either stretch or compression has taken place. Now, there's two ways you could do this, but I'm going to think of this as something has happened to stretch the graph. And when we have problems like that, we're always just going to put some a out front of here. How has this been stretched or compressed vertically? I'm going to put some I don't know out front. Now, I have to solve for that a because I'm not sure how it's been stretched. So what I'm going to do is just put in one clear point from the graph. And I haven't thought about this. I think you would have to use something other than the vertex, but I'm going to use the point 2, 0. Okay? I'm going to put this point in. So here's what I've got. 0 equals a, 2 minus 3 minus 2. Now I'm just going to solve for a, and then I will know what kind of stretch or compression I had. Now I have this. Now I get the absolute value of negative 1. Now this turns into just positive 1, and a times 1 is just 1. So I've got a minus 2. I'm going to switch sides here, but a is equal to 2. So now I know. This had a vertical stretch of 2. So I think we've seen this before, but we'll certainly see it again. If we're not sure about a stretch or compression, we put an a in front of there, and we just find one clear point from the graph. And if you solve it, you'll be able to solve for a. Hold on, I didn't put the final version of this anywhere. So 2x minus 3 minus 2. Okay, all of that's doing the same thing. And then down here at the bottom, they're saying that this actually could have been thought of horizontally as well, but I would not solve it like that. I would have just done it with the a like we did there. Okay, now this turns into just basically the stuff we were doing in the previous sections with translations. There's really nothing else here. So my initial function is x. Now I'm shifting it to the left. That's addition of 2. Okay, what else we got? It's vertically flipped. So I had to think about vertical. I always think of it upside down. So vertically is that I'm shifting it from up to being down. So those kind of flips where I'm going over the x-axis, put a negative out front. Horizontal flips would be inside with the x. I've got a negative out front, and it's vertically shifted up 3 units. Those are on the outside. Okay, so there's my new version of the absolute value function. Okay, now I mentioned this at the beginning of the video, but when we have a function like this, if we're trying to solve it, so we're looking for the zeros, the roots, whatever you want to say. When we are searching for that, then we have to work an equation. So I'm going to take you back here. So if I'm trying to solve this, everything inside of here might, now I don't know what it is yet because there's an x in there, but all of this could turn out to be a positive number, or all of this could turn out to be a negative number. I don't know what it is. And so what I'm going to have to do is I'm going to work it like it's a positive, and then, I've never shown it like this before, but this would be a good way of showing it. So this is really what's happening. We're working it once as if everything in there is a positive, but what if what was inside of there really was a negative, like this? Everything in there was really a negative. Well, what I would do is I would divide that negative to the other side, and I would work it like this. Now, I'm just trying to show you where it comes from, but if you don't particularly care, the idea would be this. You start with this original equation. You're going to work it twice. You're going to work it once just like it is. and then you're going to work it again as if that right side equals a negative. Okay, now they're asking us to do that here, trying to solve this for when it equals 0. So I have 0 equals the absolute value of 4x plus 1 minus 7. Now, if students are going to miss this, they're going to think that right now is you don't work it twice at this point. You don't work it twice like with a plus and minus right now. What you want to do, you have to get the absolute value alone, and then you're going to do that trick. So first of all, like if this is my problem area, I want to isolate that. It's always what happens with solving these equations. So I want to isolate this guy, so I'm going to send 7 to the other side. So what I have now is this. Okay? Now I switched the directions, but it's the same thing. All right, now let's solve this. I've got 4x plus 1 equals 7, and now we're going to do the trick. We're going to solve it twice. 4x plus 1 equals 7, 4x plus 1 equals negative 7. Now I'm going to jump it, so it'd be 6 over 4, which would be 3 halves. Okay? Now how about here? 4x equals negative 8, x equals negative 2. Okay, now we have found two roots, two zeros. This function hits the graph at two spots. It hits at the point 3, 2, and it hits at the point negative 2, 0. Now, why is it two of them? Because this is a v. Remember that an absolute value makes a v, and we've moved it right and left, and we've compressed it and stuff, but we've also moved it down. So if it started here, we moved it a little bit to the left and down, so it's down here somewhere. That v is going to hit the x-axis in two spots. Well, that's what we found. Okay, so we're going to try this again. So this v is going to hit, so it's been moved down again, you see, because of the negative 3. So we're going to find two spots where this v hits the x-axis. So now I'm going to solve this, but I have to get the absolute value alone before I do the trick. So what I'm going to do is send the 3 to the other side. I'm going to write it the other way. So really the 3 went over there, but so we've got this. Do you agree? So I just reversed it. Okay, now I'm ready for the trick. So I'm going to do 2x minus 1 equals 3, and I'm going to do 2x minus 1 equals negative 3. Okay, solve this. Okay, I've got 2, 0, and negative 1, 0. Those are the two roots, the two zeros, the two x-intercepts, whatever you want to call them. All right, again, not a ton of stuff, not a lot there. Just it's really important to remember when you're solving these, you have to solve them twice. Remember that mathematically an absolute value is just an abbreviation. The mathematician wanted to know how far I am away in a distance. He didn't care whether it was a positive or a negative. He just wanted the distance, and that's what an absolute value is all about.